We've been talking about buoyancy in science class, and I happen to have this old dinosaur relic left over from a time when schools could afford equipment for science classes. I don't know where it's from, 1950, 1970, I don't know. But I have it, and the way it works is I put a balloon in here, let's say, and it's sealed, and you turn it on. There's a little tape under here, little valve. Now you can hear it's suctioning. It's a vacuum chamber, and at this point it's already too hard for me to lift the bell. I'll have to really pry to get it loose. Sounds kind of science-ish. Now we're gonna hurry up and do a time lapse. All right, so we've arrived at a point where the balloon has increased 3 or 4 times its normal size. Now I'm going to turn it off and let the air back in the chamber. You'll see how the atmospheric pressure kind of squeezes it back down to its normal size. Back to little tiny. So that gave me an idea. I put a weight attached to a balloon, and right now the balloon isn't large enough, nor is the weight. The combination of the weight and the balloon are not enough to displace enough water to make it float. But if we use this vacuum chamber, we might be able to make the balloon increase in size until it floats. So we're going to turn this on, close the seal, and watch this. Watch the balloon increase in size as the pressure in the chamber decreases. The balloon slowly expands, taking up more space, displacing more water, until it reaches a point where the water displaced, there we go, the water displaced weighs as much as the object itself. And if we continue on, you see the balloon just gets bigger and bigger, so that upward arrow, if you will, you have to imagine a downward arrow for gravity and an upward arrow for buoyancy. And as that balloon gets bigger, the upward arrow gets bigger, so to balance it, the object lifts higher up in the water. So as that balloon gets bigger and bigger, the upward arrow gets bigger, which lifts it higher in the water, thereby displacing less water and balancing the force, the buoyant force, and the gravity, the force of gravity pulling down. So as this arrow gets bigger, it naturally is, if this arrow is bigger than this arrow, it's going to lift up until that arrow shrinks because it's not displacing as much water. And that just continues to happen as it rises higher and higher, it sits higher and higher in the water. And if we keep going, you'll also make another observation. There'll be tiny bubbles in the water as the water begins to almost boil at room temperature. This compressor's not the strongest in the world. If it was stronger, we could see the water, quote, boil more vigorously at room temperature. So there you have it, buoyancy. I think I'll pause the video and bring you back when it's actually boiling, or close to it. There we go. Boiling at room temperature. And the solution's not hot. It's just the atmosphere pressure around it is not suppressing the water. So it's got enough energy to go airborne, turn into a gas. Pretty cool. Science rules. So there you have it. It's a little buoyancy demonstration.